Hi, Dr. Anthony Revis here with Watch Me Work It. I'm going to work some thermodynamic problems that involve some states of matter changes. That's liquid, liquid, solid, states of matter changes. So let's work this problem. Calculate the heat needed to raise 27.0 grams of water from 10.0 C to 90 degrees C. Okay, so what we note here at 10 degrees C, that means this water is a liquid. These are things you just have to know. And this is a liquid. So this is a basic liquid transition, if you will. So no phase change here. So when you do these type where there's no phase change, is going to involve a temperature change. So this is going to be uh, here is going to be Q, or you'll see delta H. You'll have Q equals mass times specific heat capacity times delta T. Okay, so that's the way you would calculate these. All right. So what we have here for this heat, we basically put in the mass of 27.0 grams times the specific heat, and sometimes that'll be called specific heat capacity, and in some texts it's called CP. All right, some is called S, others are called C. So it varies all over the map. But watch the units will tell you. So if it says joules or joules per gram degree C, then it's talking about specific heat. And so for water, liquid water, that's going to be 4.18, and sometimes you'll see a 4 on that too, times the temperature change. And so this temperature change in degrees C was basically 90. So 90.0 minus 10.0 degrees C. And so if we put all these numbers in our calculator and punch them through, we will get 9,000, let's see, 0.3, 7.44. And then since we started with 3 sig figs here, our final square end number is going to be 9040. Here in the units are going to be joules. That's our final square end answer for doing that problem. You'll want to check this, make sure I didn't do any punch through on the calculator errors. Okay. So here, calculate the heat here for this copper. Similar process. We just basically are going to take this is going to be a non-phase change, if you will, again. So we're basically going to have Q equals ms delta T. And so we put in the mass here of this copper. I should read it again to you. We have calculated heat given off when 129.7 grams of copper cools from 155.0 C to 23.0 degrees C. Okay. And here, to do this, we have mass of 159.7, and we have and that's grams. Don't let me forget the units. And then we have the specific heat capacity of this is given at this. You'll hear specific heat capacity or specific heat used interchangeably many times. And then here, it's going to be T2 is going to be 23.0 minus this 0. Now, we'll talk about this as well. It's a good time to talk about here. When you run this through, you're going to get this value. It's going to, let me punch it through here to make sure I can get the right number. All right. Yeah, when we punch this number through, we get about 8 1115.954 on the calculator, and that's going to be in joules. And we have what, 4 sig figs working for us here. So that's going to be, and that's going to be, by the way, a negative value. We'll tell you about that in just a second here. This is going to be square in number of minus 4 sig figs. Yeah, 4. 8116 joules. And it's going to be a negative value. Now, oftentimes this is just calculated for the absolute value of it, okay? So you'll have to know how to do that depending on who's teaching whatever course you're in. But this is negative, which means that they go from the higher temperature to the lower is exothermic. It must release energy, and that makes sense, right? You must release the energy so it can basic molecules can come closer together. So this is exothermic, by the way, and that's what you also know about cooling here. So it's an exothermic process. That's what the sign says. Oftentimes they'll just take the absolute delta T, and you will have to tell them whether it's endothermic, exothermic. Okay. All right, let's do one more here. Now the next one's going to be a bit longer. All right. Calculate the amount of energy used when 33.3 grams of ice at 0 C is converted to steam at 150 degrees C. So when we do that, we have to go through a few phases here to get there. All right. So we're going to do this in different steps. All right. And each step requires its own formula. All right. So let's keep that in mind. So here, the first step, we need to take this from, we have 33 grams of ice at 0. Well, we need to get it to water at 0. So the first phase we have to get through, phase 1, is going from 0.00 ice, this is degrees C, ice, to 0.00 degrees C liquid. Okay, so let's do that one. And to do that, we need to say that Q equals, here is going to be mass times the heat of fusion, which I should have written for you on this. So to do this, this is mass times the heat of fusion, delta H fusion. And we just looked that up on a table. We have the mass at 33.3 grams. And we simply look up delta H fusion on a table somewhere. And if you look that up, that value is 33.334 joule per gram. So I apologize for not putting it right here on there initially, but that's delta H fusion. That means that's between the melt and the freeze state. So that's going to be your first one you're going to get there. And so you're going to get an answer here of 1122.2 joules. And I'm going to deal with the sig figs when in the final answer. The number of sig figs here is going to be 3 sig figs in the final answer. I'll just deal with that at the end. Okay. So the second phase we're going to go from 0.00 C to what? 1, and that's liquid, to 100 degrees C liquid. Okay, and so that's going to be a delta T. So that's going to be Q equals mass times specific heat delta T. Okay, and so we just put these numbers in at 33.3 grams times the specific heat capacity of, and this is water, liquid, so that's going to be right here, 4.18 joules. I have the units right here all together. Joules per gram degrees C. And that's going to be times your delta T. And that delta T is going to be 100 C. And barring, no obvious calculation errors here, delta T, that's T2 minus T1. I think you get that. So if you punch these numbers through, you're going to get 13919. That's a 9. 19.4 joules. And so again, we'll deal with the sig figs in the end, okay? And now we have to take this, right? And we need to take it from 100 degrees C liquid to 100 degrees gas or steam. Okay, and that's steam right here. So steam is gas. So that means we're going to say Q equals, okay, that's a phase change. So anytime you have phase change, you're going to have this fusion or vaporization. In this case, you're going to have delta H vaporization, and that's going to be vape. And you look that up on a table also, nothing magic. So you take the mass, and then you're going to have that vaporization constant, which I looked up for you on a table. Didn't write it here, but this is the value of it, straight from a table. So you get these from a table. All right. And that's going to work out to joules. That works out really nice. So this is going to be, if I punch that through correctly, or no real weird calculation errors, I'm going to just write this value down and hold on to it and deal with my sig figs at the end. Okay. Reduces the amount of error carried through and the variance. Okay. Carried through here. So we got to go here. Now we have to go from 100 degrees C liquid to 150 degrees C liquid. So that's a temperature change, not a phase change. So the way you can know which formula to use, if it's a temperature change, you use a temperature change formula. If it's a phase change, use a phase change formula. That's how we know which one to use. Okay. All right. Don't overthink it. So here we have what, well, we have temperature change, so that's mass and specific heat, and that's of steam. Oh, this should say liquid to steam. This should be gas right here. We're going from 100 degrees C gas to, I apologize for the messy, gas. If I can write a G. So this is gas to gas. I apologize if I said anything other than that. So this is gas to gas, steam to steam. All right, you're just raising the temperature of your steam, superheating the steam. All right, so we have mass time that time delta T. The mass is still the same, didn't change. We kept it. And here, the specific heat capacity of steam is 2.09. Now, sometimes you might, this is one of the things that people forget, and you'll see it even in others who will do this. They'll forget to change the steam, and they'll just write 4.18. So just be aware of that. And the units here are joules per gram. So I have those joule per gram times the temperature change of 50. And so when I punch this number through, okay, I got all these numbers that I got punched through here. I get 3,479.9 joules. And then what I'm going to do, I'm going to add all these up, okay? And I'll leave that to you to write the numbers down. But you add all of these up, add your answer here, 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 all four values. You put them all together, okay? You get something that looks pretty close. If I didn't miss anything along the way, 3679. Let's see, 103,679.6 joules. And that rounded to how many sig figs were we doing? 3 sig figs would be 104. I'm rounding it right here with 3 zeros. After that, 1, 2, 3, which, by the way, that's in joules. And if I convert that to kilojoules, that's 104 kilojoules. I'll assume you know how to convert joules to kilojoules. This is just a value of 1,000. Okay. So there you have it. The key here is you do 4 different equations, 4 different problems using 2, 3 different equations. When it's a phase change, you use the fusion or vaporization. Was a temperature change, you use specific heat, and that's how we do it. All right, got it? There you go.